Hi, Chem162. So there's a question on the homework. It's number 23 on homework 13. And this is a one of the more challenging equilibrium problems, finding the equilibrium concentrations given the Kc values. So to start with these, you want to look at your Kc value and set up this expression. So it's product over reactant. And the coefficients are used as exponents. So if you plug in your initial values for this, it says you're beginning with 0.92 NO and F2. So looking at your ICE table can help kind of organize your thoughts. So you put 0.92 for NO, and then 0.92 for F2, and then 0 for NO. So knowing that this is 0 and this is 0.92 and 0.92 squared, that's going to end up being 0. So your Q value is 0. So Q is less than K. So you're going to form products. So that means you're losing reactants. So you subtract X and add X. So notice I'm putting a 2X here and a 2X here. That's because there's a coefficient here. So for each 1 mole of F2 consumed, you're going to need 2 moles of NO, and you'll produce 2 moles of NOF. So that's one way to do that. Sometimes you'll see it as 1, 1.5. I don't really like working with those fractions, so I just stick to this way. It's a lot easier. 0.92 minus 2x, 0.92 minus x, because you sum up your columns. The initial plus the change equals the equilibrium. So then you get 2x here. So then we can go ahead and plug in your values for everything. So the K value is 7.2 times 10 to the minus 4, which equals 2x squared. And I got these reversed from the reaction, so I'm just going to swap those so it's not confusing. But it doesn't actually matter the order, as long as you plug in the right thing in the right place. So NO here on the left, NO on the left here, 0.92 minus 2x, and that's squared, and then 0.92 minus x. So looking at this, you'd have to FOIL this out, and there's 3 terms here with 2 terms each in them. So that's kind of crazy to try to do the algebra on that. So what you want to do is make an approximation. So let x equals 0 compared to the initial amount. And then to test this approximation, it has to be within 5% dissociation. So these problems are, if they get kind of intense like this, it's probably set up for that to work. And then to also know if that dissociation will work, you can look at your Kc value. This is a pretty small Kc value, so it should be a small dissociation. With big Kc's, you wouldn't be able to do that. And if you were going to move forward and do this polynomial math, you'd end up with a x cubic term. So you'd have to use a graphing calculator to solve for that. So we're going to try to avoid all that. 7.2 times 10 to the minus 4 equals 2x squared. And so let these terms drop to 0. Because the change is going to be small compared to the initial amount. So that's how you're able to do that. So you get 0.92 squared times 0.92. So then it ends up being 0.92 in the denominator cubed. So it's you can distribute that if you want, or I'm going to leave it like that so we can just take the square root. Makes it a little easier to solve. 0.779 equals 7.2 times 10 to the minus 4. Then multiply 0.779 times 0.779. And you get 0.0005606 equals 2x squared. Take the square root of both sides. And you get 0.0237 equal 2x. Divide by 2 on both sides. And so your x is equal to 0.118. So then test that approximation. 0.118 divided by 0.92 times 100. There's a 0 here, I left one out there. And you get 1.3%. So that approximation is valid. So this is an important thing to learn as we move into the acid-base chemistry. We'll have to make those approximations to avoid using crazy quadratic math. And then so our final value, the NOF, is what they're after. So you got to multiply your x times 2. So 2 times 0.118. And you get 0.236, which is about 0.24. So that's the equilibrium concentration of NOF calculated. All right, so let me know if you have any more questions, and keep up the good work.